So we've taken some time to derive the crystal field splitting patterns for octahedral and square planar coordinations, two of the three most common geometries for coordination compounds. We now need to take some time to derive the crystal field splitting pattern for compounds that have tetrahedral coordination. However, we found that it was fairly easy to do it for octahedral coordination and square planar coordination. Once we understand octahedral coordination, the crystal field splitting of the d orbitals for square planar coordination can be derived from that. Why is it harder to figure out how the d orbitals are split when you take and switch from an octahedral ligand field to a tetrahedral ligand field? Well, in the figure that I'm showing here, I have put the Cartesian axes labeled on the metal cation. Surrounding it are the green spheres. The green spheres represent the ligands. Now notice that none of the four ligands are coming in directly along any one of the four axes, or any one of the three axes. Therefore, the ligands are interacting with d orbitals on the metal cation that are not lying along the axis. So the dz squared and dx squared minus y squared are not interacting with the orbitals on the ligand. It's going on the ligands. They're going to be the dxy, dyz, and dxz orbitals that will be doing the interacting. So you expect those three to go up in energy, and the other two, which have very little interaction with the ligands, to go down in energy. And that's exactly what happens. You have a set of two orbitals that are the dz squared and the dx squared minus y squared that the ligands don't interact with. Now, based upon the idea of symmetry, the label for this pair of orbitals is no longer Eg, it's just E. So remember that whenever you see crystal field splitting patterns for tetrahedral compounds. The other three orbitals have to be destabilized with respect to the barycenter. So you see the dxz, dyz, and dxy all go up in energy. Collectively, that group of orbitals are known as the T2 orbitals. Now, there is a crystal field splitting energy associated with this called delta T, and the T2 orbitals are destabilized by 2/5 times delta T, whereas the Eg orbital, or the E orbitals, are stabilized by 3/5 times delta T. Now, since the ligands don't interact as well with these orbitals, the d orbitals, the dxy, dyz, dxz, there is a relationship that's been determined between the splitting pattern energy for octahedral complexes and tetrahedral complexes. The relationship is delta T is equal to 4/9 times delta naught. Now let's take and think about some applications of crystal field theory. They actually are going to help us determine two different things. How the d orbitals are occupied by the electrons on the metal cation will affect both the magnetism of the compound and its electronic spectra. Our initial discussions will focus on octahedral complexes, so we'll be dealing with the same crystal field splitting pattern all throughout the rest of this discussion. And we'll focus on the occupation of the T2G and Eg orbitals. Now, suppose that you had to arrange 4 electrons in the 3d orbitals of a transition metal cation that was split by an octahedral ligand field. Remembering from the past when you drew orbital diagrams to determine the magnetism of an atom or ion, what ways could you arrange these electrons? Well, the first possibility is to fill the T2G orbitals with 4 electrons. But notice 2 electrons have to be paired up in the dxy. Remember, we still have to follow Hund's rule, which says we put 1 electron in each of the orbitals before we start pairing up. However, that suggests the possibility 2 is the more correct one, because you still have these 2 d orbitals that are unoccupied in possibility 1. This leads to the idea known as spin state. There's 2 different spin states that we're going to talk about, low spin and high spin. Possibility number 1, which is shown right here, shows the low spin state. The total energy of this electron arrangement must be equal to 4 times the energy associated with the collective T2G orbitals minus the pairing energy. Pairing energy is the energy required to spin flip this electron and pair it up with another in a previously occupied orbital. When you have this spin pairing of 2 electrons in the T2G set before occupying the EG set, this is known as the low spin state. We need to talk a little bit about what pairing energy is first, though, before we continue our discussion. Pairing energy is the cost that an electron has to pay to pair up 2 electrons in 1 atomic orbitals. Pairing energy, which is represented by the letter P, is the energy associated with pairing 2 electrons in the same atomic orbital. There are 2 contributors to the pairing energy. One is the repulsion of electrons that, when they're put together in the same atomic orbital, because they have same charges, so they're going to repel one another. The second contribution is that requirement to spin flip 1 electron. To change the spin orientation of that second electron, that's known as the exchange energy. So, low spin arrangements. Low spin arrangements come from transition metal complexes where this crystal field splitting energy, delta naught, is greater than the pairing energy. Okay? So if these d orbitals are split by such a great amount that it costs less energy to spin flip that electron and pair it up with another in a previously occupied d orbital, the low spin state will be preferred. D electrons assume this low spin state when placed in a strong ligand field. So what I'm suggesting is that certain ligands lead to varying degrees of splitting of the T2G and EG orbitals. Strong field is a theoretical term that is associated with crystal field theory. So some ligands split the d orbitals very effectively and always lead to low spin complexes. Other ligands split the d orbitals very poorly, leading to another type of arrangement of the electrons.